Click on go.
Okay, welcome back to the afternoon session. It's my pleasure to introduce Mao Zeng from the University of Edinburgh, which will speak about review scattering amplitudes and gravitational problem. Please take the lead.
Okay. I'd like to thank the organizers for inviting me to speak. It's a great pleasure to be meeting all of you from many different fields. Give an overview of scattering amplitudes approach to the gravitational two-body problem. So basically, we take quantum field theory scattering amplitudes and deduce post-Minkowskian expansions for the two-body problem. So I'll go over a little bit of background, very quick, and then I'll talk about how okay, this laser is really okay. it's visible. How to connect quantum amplitudes to classical physics. I'll talk about techniques for computing these quantum amplitudes in the first place. Basically divided into integrand techniques and integration techniques. I'll talk about the results, and I'll talk about various developments. So this field has exploded in the past few years. This is going to be a very incomplete overview. I'm probably missing a few hundred citations. Mostly concentrate on some of the conceptual foundations of the field rather than keeping track of every latest development. So I don't have to mention in this audience that there has been an exciting program, gravitational wave direct detection since 2015, which addresses many different physics issues: strong field GR, nuclear matter, BSM, compact objects, black hole formation, population, etc. And 90 events were already available in late 2021. And we have a large number of future detectors coming up online, both ground-based and space-based, and some innovative atom interferometer-based designs, which will push the frontier of the field. So in particular, the signal-to-noise ratios will go up significantly, and that will present challenges to us theorists to improve the predictions. I think so. Previous speakers have gone over this, so I'll skip it. And that's how the usual waveforms look like. They vary significantly in the duration. Basically, it boils down to some shape that looks like this. And we will concentrate on the in-spiral regime, which can be treated by perturbative expansions, such as post-Newtonian expansion, post-Minkowskian expansion. And there are also other expansions like the cell force expansion, which goes beyond the strict perturbative regime, although with the requirement of a large mass ratio. And there are resummation methods, like the effective one-body method, and there's also semi-analytic models like IMR phenom, which you heard about. Okay, and of course there's merger and read-down phases, which people have mentioned, which I won't cover. To introduce the post-Minkowskian expansion, just a recap on what the post-Newtonian expansion is. So here's the Hamiltonian normalized over the reduced mass. That's what Newton had a few hundred years ago. And then we jointly expand in the squared velocity over c squared. I'm setting c equals 1 because I'm a particle physicist. And gm over r, they are locked together by Virow's theorem or just by the circular orbit equation of motion. So the first Newtonian correction was obtained as early as 1917 and systematized by Einstein, Intel, and Hoffman. you have order G corrections, you order B squared corrections, and mix G times B squared corrections. Okay, and it has been a very successful and long program to match up the orders. And last completely known order was 4pn, although 5pn and 6pn, a lot of it are already known, maybe a few missing coefficients still to be calculated. The post-Minkowskian expansion is just it's something that's very natural for people doing particle physics, relativistic quantum field theory, to expand in coupling constants while keeping exact velocity dependence, like we usually do when calculating scattering amplitudes in quantum field theory. And it can be, we can talk about both scattering and bound states, but scattering is particularly natural because without the Virus theorem, in scattering orbits, B squared can be large, and it absolutely makes sense to keep exact dependence on these. For example, a gauge invariant observable is the scattering angle as a function of the two masses and the impact parameter, i.e. the transverse separation. The first order angle was very easily obtained. The next order was available in 1985, and it took more than 30 years for us to obtain the next order, and that will require our new methods based around scattering amplitudes, which I will get to. So I should mention that this field has been most active in the last few years, in the sense that we are already connecting with quantities that are somewhat of interest to real experiments. But the idea is a very old one. It's from the 50s and the 70s. In particular, the paper by Iwasaki recomputed the first post-Newtonian potential from quantum field theory scattering amplitudes. Okay, and then I should also mention related methods that are in the quantum field theory framework. In particular, the effective field formalism of NRGR, which Ricardo talked about. And this was founded by Grossberger and Rothstein in 2024, and soon generated by Rafael Porto to the spinning case. And so they use a worldwide effective field theory. So the gravitons are propagating fields like you have in quantum field theory, but the matter or the black holes or neutron stars are semi-classical world lines. What we do is treating everything as dynamical fields, including the matter fields, and early. And this connects to very exciting modern developments in scattering amplitudes, which I will only mention briefly. In fact, before this field became hot in the last few years, in 2013, Duffy and Rothstein already wrote an early paper which explored modern amplitude methods such as generalized unitarity and double copy. The only essential difference was that they applied it for the post-Newtonian expansion rather than for the post-Minkowskian expansion. And also soon after the paper, Varun Vaidya wrote a paper which generalized to the spinning case, and in fact he used a minimally coupled spinning matter fields, which received lots of renewed attention in the last few years. Okay, so I should mention that although LIGO, Virgo, Cagra, the detectors usually deal with merger events, scattering orbits have also received interest in the GR community. For example, Thibaut Damour has written papers on using scattering as a method to do do UV matching. For example, if you compute a gauge invariant observable, like the such scattering angle, as a function of the masses and the spins of impact parameter, etc., you can ask the question: how can you deform the Schwarzschild metric and the corresponding Hamiltonian to reproduce the same angle for scattering orbits? And then the same EOB Hamiltonian can be applied to the bound case. So that's one way to do it. Okay, and so phenomenologically, there are hypothetical hyperbolic encounters which might be observed in future. People have speculated in environments like globular clusters with lots of black holes. Maybe every now and then you can get a close encounter of two black holes. And also the results can also be related to transient signals to high eccentricity boundaries, because the large eccentricity expansion is basically coincides with the post-Minkowskian expansion. They share the feature that the visual theorem is not very helpful. And also there have been interest in the self-force community to calculate the first or even self-force corrections for scattering observables. And it's in the last few years, the scattering amplitudes approach have really made some impact, and so that relies on many developments. So there are several methods to that allows you to translate scattering amplitudes and quantum scattering amplitudes to classical observables. The caveat is that the easiest one to get is classical scattering observable, i.e. in unbound orbits. You can use several techniques, which I will get to. I'll mention the names: ICTP, non-relativistic EFT, heavy mass EFT, and this K-Mock formalism based on observables in the computed with the F matrix. And this loop integrand. So basically, since not everyone is doing quantum field theory, I'll just mention that beyond the lowest order, an amplitude in quantum field theory is an integral over space-time, either in configuration space or Fourier space or momentum space. So you need an integrand and you need to do integration, and both can be very challenging with traditional Feynman diagram methods. But the modern scattering amplitude methods have revolutionized both of these areas. Techniques such as generalized unitarity and double copy. So the double copy is in particular very relevant in the gravitational context. And so there are techniques for dealing with massive matter fields with spin. That's the spin-helicity formalism, initially for massless scattering, but generalized to the massive case by Hamid, Wang, and Huang in 2017. Also, there are also ways to make things more tractable within the Feynman diagram approach, with a little bit of tweaking using nonlinear gauge fixing to make the Feynman roots more compact. Okay. Then loop integration techniques is something, and this is an area which have received lots of attention for Collider physics. The kind of mostly in the context of the LHC program. Techniques such as integration by parts, differential equations for Feynman integrals, method of regions for doing asymptotic expansions, which have been applied to this field in essential manners. And also, we can address not just scattering observables, but also bound state dynamics. For example, if you match to some potential in a non-relativistic EFT or effective one-body formalism, you can apply the potential extracted from the scattering case to the bound case, and we can do it by analytic continuation without going through an intermediary like the potential. Under certain conditions, the observable as the functional form of the observable as a function of the energy can be analytically continued from positive energy to negative energy, i.e. from the scattering case to the bound case. Okay, and so here's this diagram. Just to recap, the post-Newtonian expansion goes in this diagonal way. We always go down, whenever we add one more order in G, we also want to add one more order in V, while the post-Minkowskian expansion goes down this way. And the 2019 third post-Minkowskian order result, I think it was one of the results which caught people's attention and started to make the community aware of the power of the scattering amplitude methods. And so it took more than 30 years to go from 2 p.m. to 3 p.m., but only 2 years to go to the next order, since we are only starting to exploit the power that is brought by the new formalism. And so the world line methods have also been adapted to do post-Minkowskian expansion rather than post-Newtonian expansion, most notably by the group of Raphael Porto and his collaborators. So both of our results have been subsequently reproduced by Porto and friends. And in the case of the fourth post-Minkowskian order, they have, at least temporarily, even gone farther than what we have, and they have done it completely, including all the both conservative and dissipative case in terms.
Sorry, question. What advantage of being all this? I've seen some of these claims in the past. The following. So you said 2 years from 3 p.m. to 4 p.m., but it's also conservative, so it's not fully known. And then do you expect that rate to maintain, and if you go to 5 p.m.? As I said, I have heard things like this before.
5 p.m. is challenging. We are looking at it, and Raphael Porto and friends are also looking at it. So it depends on how we make progress. It may be next year, it may be in 5 years, but
can I qualify the question? So how many new master integral do we have at 5 p.m. with respect to 4 p.m.? How many new master?
Okay.
Well, if you're saying it later, forget it.
I think 4 p.m. is order 100 master integral. 5 p.m. will be order a few thousand.
But the key question is, among those few thousand, will be there someone who has not been ever solved before?
The master integrals itself won't be the most challenging problem. It's to getting their coefficients. Yeah. Okay. But I'll also talk more in the end about it.
I mean, there was another point in the question. So you said 2 years to go from 3 p.m. to 4 p.m.
Yeah. So the conservative part includes both the so-called potential contribution and the tail contribution. So that we included the conservative part of radiation reaction also, and that shares lots of features with the calculation involving radiation, involving dissipation. So we haven't done the complete dissipative calculation yet, but another group has done. Yeah.
So the 4 p.m. is fully known?
It's fully known now for scattering observables. That's the up to 3 p.m. it's straightforward to analytically continue from scattering to bound observables. At 4 p.m. the new feature is that there are non-instantaneous tail terms which cannot be analytically continued in a simple manner. But that's still an active area of research.
Thanks.
Okay. So now I'll explain how it's possible to use scattering amplitudes to make predictions for the classical two-body problem. So first, how do we go from quantum to classical? As Ricardo mentioned, a very good tool is effective field theory. And whenever you deal with a problem that involves a large hierarchy of scales in the framework of quantum field theory, it's a good bet to look at the effective field theory framework. So effective field theory is a way to systematize the expansion over some large scale ratio parameter. Here, the first thing to talk about will be the point particle effective field theory, when the black hole or neutron star sizes are much smaller than the separation. Basically, that's the case in the inspiral regime. It's this point particle approximation that makes it possible for us to translate the problem into the scattering of point-like elementary particles in quantum field theory. In particular, they are scattering amplitudes. For example, in the spinless case, we just have the Einstein-Hilbert Lagrangian minimally coupled to massive scalar particles. And for people who are not doing QFT, this is nothing but a wave equation. It describes a particle propagating with the speed of light if there's no mass, or some relativistic dispersion relation with the mass term. And so, as I mentioned, the point particle approximation is not an ad hoc approximation. It's just the lowest order in this systematic EFT expansion, and correction will be given by the finite size correction terms in the Lagrangian, which are sort of made of higher order or higher dimensional operators. For example, specific to the scattering amplitudes formalism with dynamic matter fields, we have finite size terms. Just couple this phi field to the graviton field in a more non-trivial manner. You have a pair of biotensors, and there are two different structures coupling phi squared to c squared. So the lowest order Feynman vertex would be a 4-point vertex coupling two matter lines to two graviton lines. In the world line formalism, people have also wrote down the expressions and they called it electric and gravitomagnetic coupling, and they can be translated into also this formalism with dynamic field, and they are highly suppressed in general by power counting, just like in the world line story. And even more so by black holes because of the accidental vanishing of love numbers. Did you raise your hand?
Yes, yes. So why you jump from 0 derivatives to 4 derivatives? What happened to 2 derivatives there? So now you get a Riemann square, phi square. But then you can have Riemann square, phi square, then you could have the Riemann square, phi square with 2 derivatives instead of jumping to 4. Why you do the...
I haven't gone through the argument, but it's basically by EFT operator counting and eliminating redundant operators by equation of motion. But
I don't see no, because if you integrate by parts, it gives you box phi, but then it gives you also derivative of the Riemann, so it should be there. Yeah, okay, but modulo Ricci is the Riemann. Unless you think that that object there is, you can trade it for a Gauss-Bonnet, and so it's topological. The Riemann square is Gauss-Bonnet plus Ricci. But then
It's multiplied with Ninos. If it's multiplied with Ninos, it's not so.
Yeah. No, but that's what I mean. Maybe the d phi, you get rid because when you integrate by parts, you can. I don't know.
okay,
We can check it later.
Yeah, I should look at it offline. Thanks for bringing it up. Okay, so now I talk about the classical scaling of amplitudes, i.e. the classical limits. How do you send h bar to 0? the classical limit is the correspondence limit of quantum mechanics. That's when all the charges, all the quantum numbers become large. For example, the angular momentum in the hydrogen atom, the angular momentum is quantized in units of h-bar. And for a classical system, we need the orbital angular momentum to be much larger than h-bar. This J over h-bar, that's roughly equal to the momentum times the separation. And if we consider a generic relativistic setting, because we are not doing post-Newtonian expansion, so there's momentum and mass are of the same order. I mean, they differ by c, which is 1. Okay, and this r by a Fourier conjugate power counting, this r is basically of the same order of 1 over q. The typical graviton exchange will have momentum 1 over r, the Fourier conjugate to each other. So now the final conclusion is that n over q should be much greater than 1. So you are scattering two very massive particles, but the exchanged momentum should be very soft. So if we consider the masses as order 1 parameters, then we can rephrase the classical limit as the small q limit. It's the small momentum transfer limit of quantum scattering amplitudes. Then in quantum field theory for the 4-point amplitude, people like to talk about Mandelstam variables. So this, in the language of Mandelstam variables, this is the limit of small t. So t is defined as q squared. And now we have to realize that although in quantum field theory, we often talk about tree level being classical and loop corrections being quantum corrections, that's not the case here. There are many ways to see that, why it breaks down for our context. But one way to see is that if you go to QFT textbooks, you can see that they count powers of h-bar from the propagators and vertices of Feynman diagrams. If you do the power counting with some graph theory, simple graph theory arguments, then you can see that every loop in the graph adds 1 more power of h-bar. But what we are doing here is something like the QFC scattering amplitudes, but for particles with extremely large masses. And the loop integration can also be dependent on these mass ratios. So, because these terms also arise in loop integration, it changes the conclusion completely. Now, the conclusion is a bit unfortunately is that at every loop you get a 1 over h-bar divergence. So there's no smooth classical limit until you do some proper subtraction. The intuition you can get from, for example, the WKB or JWKB. Some mathematician J was did a few decades before WKB. So it's basically you have a quantum particle through a shadow potential. You get an amplitude oscillatory in the oscillatory regime. It's something like this. And if you do the perturbative expansion in QFT amplitudes, what you end up with is expanding out the exponential as a Taylor series. You get worse and worse divergences. And so people have given funny names, such as this super classical terms or classically divergent terms. They are really an artifact because we are not calculating the right thing. So how do we extract finite classical quantities? There are a few methods that I show below. One is the Eichner exponentiation. It's not necessarily what's most used in modern loop calculations in the recent few years, but historically it's a very important approach going back many decades. So you think about iterated scattering. So we have some scattering with a small exchange momentum because we are working on the classical limit. And so, and the classical exchange of momentum, for example, you have some a deflection angle, which is small but still finite, let's say 5 degrees or 10 degrees. The impulse or the change in momentum is a classical macroscopic quantity, definitely not a quantum quantity like h bar over r. So the classical momentum transfer is built out of a huge number of quantum graviton transfers. And fortunately, we don't have computational power to calculate Feynman diagram with a billion graviton exchanges. But fortunately, they fall into some simple iterative structure. And the dominant contribution comes from the regime where each momentum transfer is nearly transverse in order to keep the matter line on their mass shell. Otherwise, we get some off-shell matter particle that's like a virtual particle in quantum mechanics, in quantum field theory, and that corresponds to short-lived fluctuations, which are highly suppressed. So we have this kind of iterated on-shell exchanges, and the amplitude just exponentiates, and it's most convenient if you do the Fourier transform from Fourier space to impact parameter space. Then the amplitude can have some exponentiated structure, which captures, in particular, this one over h bar will sit in the exponent, and it will be exponentiated explicitly. And now we can extract a scattering angle from it. So there are rigorous derivations based on like steepest descent of stationary phase approximation. But some simple intuition can also be can already be obtained by undergraduate optics, the Huygens principle, because scattering the wavefront travels normal to the phase gradient. So if your scattering phase has a dependence on the impact parameter, then this non-zero derivative causes the wavefront to deform, and that's exactly proportional to the scattering angle, at least at lowest order. So that's the basic idea of how you get observables out of the scattering. Out of this ICO, the so-called ICO, and spin generalizations is an active frontier of research. I don't think a fully satisfactory proposal has been laid out yet in the spinning case.
So to get the scattering amplitude means now you're going to have to compute this delta. Is this delta simply constructed from Feynman diagrams? Is that the point?
So the point is that we first compute the scattering amplitudes, then we do some processing to get a finite quantity. We usually calculate amplitudes in momentum space, then we transform to Fourier space, then we take its logarithm to get this exponent, which is known as the ICO. And this makes the divergence much tamer, but still there's a little bit divergence, which is fully cancelled after you take the derivative. So it's then after a few steps of processing, we get a finite quantity.
Yes, the question was more like it was simple constructed the delta from Feynman diagrams, right?
Yeah, the question was basically you were saying that the challenge is that you can't do this large number of iterative transfers. So presumably to calculate the scattering amplitude, you must be able to calculate that from a single transfer or some simple.
Oh, yeah, that's right.
Right, and that's the part I missed. So
yeah, that's right.
It has been understood.
Okay, so by doing a single transfer or by doing one or a few Feynman diagrams, you can then calculate.
Yeah, so if you know in advance that your amplitude is of this form, then by doing one or two orders, you can match the required and determine the coefficient.
I see.
Okay.
Yes.
No, sorry, maybe I'm lost. I'm bringing something that's completely off tangent here. But Huygens principle in GR doesn't point, just, is it because you're doing something that's completely different that you don't bother about that, or at some point this would come in and raise its head?
It's really just intuitive argument, which works at the lowest post-Minkowskian order. In post-Minkowskian expansion around flat space-time, we are not really talking about curved space GR.
Sure.
So we are by order in G. It's like a flat space perturbation theory. Yeah.
But then that is something you're going to be able to appeal to at the lowest order, but in a higher order, which
there are rigorous derivations like this descent of stationary phase approximation, which becomes important at the third order in G. So there are some little bit of kinematic corrections to this formula. But yeah. Other than that, it should hold to all orders. Yeah.
No, I have a comment on this. Of course, it's not the first time I hear talk about scattering for gravity, and every time people bring this argument, but I cannot avoid thinking in the back of my mind that this is something that in field theory people see in the standard field theory, quantum field theory courses. Is that basically you have to keep the connecting piece of the diagram, just because the effective action is the logarithm of the partition function.
Yeah.
Because if you take all of the partition function, you get iteration of fundamental processes that you don't want.
Right.
So that's the origin of the superclassical terms. And when you take the logarithm, that's what you do. Basically, you get rid of the superclassical terms, just because they are iteration of fundamental processes that shouldn't belong to the effective action. Of course, you don't have an action. You don't work with the effective action.
The specific iteration, that extra iteration. It's all extra.
Yeah, but basically, if you look at from the point of view of effective action, you're just removing the iteration of fundamental processes which are not connected diagrams. And you shouldn't take.
Yeah. I think it's made manifest in the world line approach. Then these matter propagators are fake. Then you are literally just multiplying separated diagrams.
I mean, it's nothing exotic at all.
Yeah, that's right.
People do it all the time.
Okay, yeah, that's right. Okay, so other approaches, we can write down a non-relativistic effective field theory. Now we have a linearized rather than quadratic kinetic term, because we are not interested in antiparticles in the classical setting. And so this is the action for non-relativistic particle, two particle species interacting via some potential. Here the potential is instantaneous, but non-local in space. So if we compute scattering amplitudes in this in effective field theory, the final diagrams look extremely simple. So actually, I'm putting one of the matter particles as spinning, but it doesn't matter. So you just get these iterated bubble diagrams, which in contrast to this full theory diagram, which in itself is an effective field theory, is the point particle field theory. But now we treat this as a full theory. It's a theory of interacting scalar fields and graviton fields. If we do some EFT matching, we need to require the two amplitudes to be equal to each other, and at least to the order of the approximation that's kept by your EFT. And so in the EFT literature, this is known as on-shell matching, and this fixes the interaction potential. And this non-relativistic EFT potential is exactly the classical potential in some specific gauge. Okay, and another formalism known by the name of this author, known as the KMOC formalism. It's based on S matrix and with a wave packet. So you want some wave packets that looks like classical scattering. You want them to be semi-localized in both position and momentum. And of course, due to the uncertainty principle, you cannot do the localization too extremely for either position or momentum. So the middle ground is known as the Goldilocks condition. The quantum wavelength of the massive star should be much less than the wave packet spread, which in turn should be much less than the impact parameter, the separation of these two bodies. And we have just a plane wave state with a transverse displacement of magnitude b. We now just so this is in state, which will evolve to an out state in quantum field theory, using the S matrix terminology. So this S matrix tells you how the initial state becomes a final state in quantum field theory. And now we insert a measurement operator, some permission operator, to measure whatever we want. So this can be a classical observable, for example, the momentum, the change of momentum after scattering, or known as the impulse. So a little bit tricky point, which used to be controversial at some point, was that in the K-Mock formalism, you are evaluating this S matrix order by order in perturbation theory. You are not implicitly considering the summation like in the Eichner approach. For example, you write down a Feynman diagram like this. This gives you a finite low-order perturbation theory. For example, if we want to measure the momentum carried away by the graviton, it's this graviton, L, then I insert L mu as my measurement. So that comes from my measurement operator, and we integrate over phase space. That's what we calculate. But because this is done in fixed order perturbation theory, now we are seemingly considering momentum transfer that's literally h bar over r, which without iteration doesn't give you a full macroscopic classical momentum transfer. But this issue has largely been addressed subsequently after the initial paper. For example, if you assume that this S matrix itself has an exponentiated form, and then that's the only modification, and we still use this same formalism, we still use the same wave packet states, just plugging in this formula, we can rederive the Eichner result. Yeah, also high order calculations, for example, the complete conservative plus distributive dynamics at 3 p.m., which we computed within the K-Mock formalism, with other approaches. So I think now it's beyond reasonable doubt that the K-Mock approach is absolutely correct. I think there are many ways you can understand this. One way I understand it is is some intuition from Ehrenfest's theorem in quantum mechanics. So there are certain equations that are independent of a true classical limit. For example, the expectation values of x and p have evolution equations like this in quantum mechanics. They exhibit something like the classical equation of motion, even if you don't properly prepare a wave packet state that is truly classical-like. Okay, so these are.
I have a question. Can you look at this before you go back one slide? You were mentioning having to construct a wave packet instead of particular properties, but it looks like this in-state is just a plane wave. So
okay. So
where is the actual wave packet?
So the plane wave packet, you can also consider like a Gaussian profile in the case, but once we get to the actual calculation, a plane wave packet is sufficient.
Sure.
Yeah, I forgot the exact reason.
I don't understand what's the purpose of the condition. Is that condition somehow enforced by the form of this plane wave, like some scaling of the impact parameter versus QT, or what?
So one non-trivial, let's say, emergent feature of K-Mock is that the exact shape of this wave packet doesn't matter. We know generically it's some plane wave states with some eventually some exponentially decay profile to suppress it, but exactly how it decays doesn't really matter. And when we get to the actual calculation, this plane wave profile is sufficient, and all the other details will
Is
drop
this
out.
just the usual assumptions about the wave factor to allow you to define the scattering problem as the scattering of in-states to out-states? Because usually in the normal derivation of scattering, you have some in-states and out-states, you actually calculate with plane waves, but in order to have the true separation from in to out-states, you assume some localized wave factors at the start, and you throw it away. Is that basically the same?
Yeah, I think if you go through the derivation, a proper definition of the wave packet shape just drops out. Yeah.
I understand. Thank you.
Okay. Okay, and I don't have much time to go over this, but I should briefly mention that you can also go from scattering observers to bound state observers by direct analytic continuation, initiated by Gravitational and Raphael Portal. And this generalizes. This so far only works for instantaneous the case, which can for observables that can be reproduced by an instantaneous potential. It generalizes straightforwardly to aligned spin cases when there's no orbital precession, and for non-aligned spin, I think some people like Ricardo Gonzo in the audience are actively working to make this analytic continuation possible. Okay, now we talk about the actual some techniques to actually get to these quantum amplitudes. The loop integrand first. So this directly relates to traditional Feynman rules in the traditional way of computing scattering amplitudes. To get the Feynman rules, you need to perturbatively expand the Lagrangian in weak field limits. For example, the Einstein-Hilbert Lagrangian. You do a Taylor expansion in this small h. So the linear term is basically some total derivative. It doesn't really matter. The second order term will be the Gravitational propagator, like in the like in some free fields theory. The cubic term will be the non-trivial first interaction term. And if you do it for the Einstein-Hilbert action, the cubic term is extremely large. So as the traditional Feynman diagrams become very difficult. So in the modern developments, known as the double copy, significantly simplify these calculations. So it's simplest for the 3-point amplitude. So I won't explain the details, but the graviton amplitude is just a square of the Young-Mills amplitude. Once you go to 4-point and above, it's a little bit more complicated. You can either use Llewellyn relations from string theory, or modern incarnation known as the double copy. So generally, you have a sum, and each term is a quadratic expression like a square. So this double copy version is actually usually a little bit more friendly to these amplitude calculations. Okay, I don't have time to really get into the details, but a double copy is a huge field by itself. And there are all sorts of variants of double copy, and several variants attempt to directly target the classical limit. But I don't think any of them are as fully developed as in the scattering amplitude case. And then the essential technique is generalized unitarity, which tells you that the loop integrand can be reconstructed from tree amplitudes. So the loop amplitudes, which gives higher order corrections in G, can be constructed from much simpler objects, which are the tree amplitudes, by generalizing the optical theorem with some tricks like allowing the loop momenta to live in a complex plane. But yeah, again, I don't have time to go into the details, but I should mention that this works even better in the classical setting than the fully quantum scattering amplitude case, because for fully quantum scattering amplitudes, there's this little annoyance called wave function corrections, especially for a massive lag. this wave function term in the LSC reduction formula cannot be neatly described by the generalized unitarity method, but these terms are of no relevance for the classical limit. For the kind of amplitudes we calculate to extract classical observables, generalized unitarity is a perfect method. Okay, now some words about loop integration. The kind of loop integrals we handle are very complex. So people have calculated similar integrals in Barbour scattering for Kleibers. So in Barbour scattering, you are scattering massive particles like electrons, and you are exchanging massive particles like photons. So it's exactly the kind of amplitudes we consider. For us, the massive particles are point particles representing black holes or neutron stars, and the massive particles are the gravitons. So the class of integrals are very similar, but they are extremely difficult for the full quantum case. But fortunately for us, we are interested in the small momentum transfer limit, which is the classical limit. So we can do this method of regions to expand our loop integrand before we attempt to do the loop integration. The only region of interest of the classical limit is the soft region. So if we the soft region is basically a dictionary that tells you how each external and internal momentum scales, and it tells you how to do the Taylor expansion. If you follow that, get an expanded integrand, and you do the integration, you get this. You get your result. Okay, and in the last few years, we have introduced several techniques that are widely known and very successful in Kleiner calculations into gravitational calculations. For example, the techniques of integration by parts and the techniques for differential equations for finite integrals. They can be used to compute these integrals in the post-mean to target the post-Minkowskian expansion. So the differential equations are essentially with respect to the velocity. So your integrals, you differentiate them against velocity, and the right-hand side can be written as the same integrals rotated by some matrix, and the boundary condition for your differential equations is exactly the kind of integrals you encounter when you calculate the post-Newtonian expansion, for example, in an RGR. So in the last few minutes, I'll just mention the kind of results we obtained. At the third post-Minkowskian order, that's our effective potential. The effective potential, it's simple enough to fit in a few lines. And it's basically some rational functions of your kinematic observables. For example, this sigma is essentially the gamma variable. That's the rapidity separation. So most of it is just rational functions. The most complicated piece is just an arcshine, and if you do a variable transformation, it's actually just a logarithm. And if we go to the next order, the calculation becomes more complex, but the final result is still very simple. So the most complicated functions that appear are polylogarithms. These are very simple polylogarithms by the standards of loop calculations for Kleiner physics. They are of transcendental weight 2. For example, simple things like Li2. Then there are simple elliptic integrals, completely elliptic integrals of the first and second kind appearing in the expression. Okay, before going into some intricacies, like the cancellation of some divergences that produce this term, I'll just show you some plots first. So this is some comparison of the scattering angle, the conservative scattering angle versus numerical relativity. So this is from a specialized numerical relativity simulation. which is for the unbound rather than bound orbits. The numerical relativity data is the black points and drawn by dashed lines, and the successive post-Minkowski and order predictions, first order, second order, third order, eventually fourth order, are shown here. And then also the same result with EOB resummation on top of our post-Minkowski result is shown here. So basically the group of Carlo et al., they worked out how to do an EOB resummation on top of post-Minkowski expansion. So it can improve the result further. Okay, I should mention that the scattering angles plotted here are very large, like it's going from 60 or to even 160. So these are not really small angles. We expect the agreement to be much better for small angles. Because,
It's a question. This is, I'm confused. What is it that being compared? Is it numerical relativity of a scattering problem?
yeah, that's right.
Or okay. And the amplitude calculation, does that include the symptom effects?
Yeah, so not in this plot, but subsequently it has been included. So yeah, I'll just mention that dissipative effects, like it was like for example, radiation reaction and energy loss and the angular momentum loss have been subsequently worked out.
Right, I'm trying to understand that plot. So that plot doesn't have dissipation in the amplitude calculation.
Right, that's right.
The relativity data does have it.
Yeah, that's right. Yeah, okay. Yeah, so there's actually another plot which does incorporate dissipation for the amplitude calculation. So that's, yeah, so that's another plot from a recent paper by Gravitational et al. So it's again for scattering observable, and then they compare with the complete scattering angle, including both dissipative and conservative and dissipative effects, and also optionally including EOB resummation. So I think that's probably the only plot that I'm ready to show. Basically, it shows that when you go from 1, 2, 3 to 4, you can see very clear improvements with respect to the numerical relativity results.
Yeah, but the EOB resummation does most of the improvement, right?
So
I mean, the dashed line is for
dashed line.
Just the dashed lines. It's not that at a low L. It's not that much of an improvement compared to where you need to go, I guess. But
yeah, I mean it's at least in the right direction. It's getting closer, but EOB improves things a lot. Yeah, I mean I don't have a good feeling for it, but they bring results that from the match to the Schwarzschild limits in the probe mass limits. So probably they, even if ad hoc, they get lots of things right in their resummation. So yeah.
And so it's actually pretty flawed. Does it look? Maybe it's reading the previous plot that it gets worse or?
It doesn't get worse.
So it gets.
It still gets closer.
Okay, for about 5 minutes.
Okay. Yeah, so yeah, sure. So I don't have time to go other things. I'll just mention we're exploring if it's possible to do for loops of 5 p.m. The answer is uncertain, but what we can say is that we can do it for the much simpler problem of classical electrodynamics. It's actually not completely trivial. The result is in terms of interesting special functions known as cyclotomic polylogarithms, which have found use in quantum physics calculations. There are many developments related to Spain. And so I don't have time to get into that. In particular, with Fernando and Manfred in the audience, we made the first calculation of spin effects at third post-Minkowskian order based on scattering amplitudes. And also there have been very active work based on world lines. And at least at the moment, they are ahead of us for this spinning dynamics. And for radiation and dissipation, there have been lots of work, both in the scattering amplitudes formalism and world line formalism. And that's what's behind the plot I showed earlier.
Why two plots? It's the same thing. So one is triangle and the other is.
I think there's some different parameters, some slightly different parameters.
So one has a different.
Yeah. Okay. Yeah, and then people have actually worked on waveforms. That's a scattering waveform, and so it's an exciting new development. Although it's not totally clear how easy it would be to extend it to bound state waveforms. Okay. So in conclusion, QFT scattering amplitudes is a new approach, and it has been successful in obtaining new results for the post-Minkowskian expansion in binary dynamics, and it complements existing approaches like classical approaches, NRGR, and also other approaches like self-force. And the developments relied on synthesizing many modern developments like on-shell methods for scattering amplitudes, double copy, effective field theories, loop integration methods from applied physics. And the scattering amplitudes framework can address many questions like spin, tidal effects, dissipation. And we hope we can be part of the effort to prepare for the coming decades of gravitational wave physics. Thank you very much.
Any question?
So basically, the electromagnetic exercise that you did is propedeutic for the gravitational one.
Yeah, that's
you already computed all the diagrams that doesn't have self-interaction in the back.
Yeah, that's right. Yeah.
And those ones are a major obstacle, or I mean, how? I mean,
the full gravitational case will be more difficult, so we are thinking of breaking up the calculation. Maybe we will look at the lowest self-force expansion term within the post-Minkowskian expansion.
But then, at G5, you have the obstacle that we are hitting at the which is the three radiative, the interaction vertex with three radiative gravitons that will enter G5. And that's trickier than what you, I mean, that's qualitatively different from what you've done so far. Because that has been a stumbling block for us, but I mean, we're solving it. I guess you will also.
Yeah, we are doing the potential region first. Yeah, then we are looking at radiation modes, and yeah, I think it's going to be difficult. We'll do the simplest pieces first. Okay.
Questions? Yeah, okay, let's thank Mao again.
No, wait. Just repeat that. If any diagonal involved, if I compare three values, so G5 we meant G4 is there. No, any diagonal in there.